Hello, thank you for staying. This talk is about the RSTT model, Regional Seismic Travel Time Model. It's work that is being done primarily by my colleagues Rajiv Ranasinghe and Mike Bonneau at Los Alamos in collaboration with Steve Myers at Livermore and Brian Young at Sandia. Many of the people in this room are fully aware of what the RSTT is, but just a quick reminder, especially for people who are less familiar with it. It's a global model that rapidly predicts travel times for regional seismic phases. So we're targeting PN, SN, PG, and LG. And the model itself accounts for the MOHO, crystal and crustal layers, sedimentary layers, surface and water and ice layers, and the 3D crustal and upper mantle structures. The models use a model grid constant. The previous models used a model grid of 1 degrees globally. And the PN travel time in this paradigm is calculated. You can see the little figure on the lower right-hand side of the slide, where we have two legs, one downward going and one upward going, which is travel time through the crust. And then we have propagation through the mantle as a head wave. But we have to accommodate the upper mantle gradient. So in addition to the mantle velocity, we are calculating the gradient, which is gamma in this particular rendition of the equation. So grid refinement for RSTT begs the question of where can we do a better job than 1 degree grids? There are places in the Earth where we have a lot denser ray coverage than just the requisite number within a 1 degree cell. Jordan Babikoff et al. In 2022 implemented data-driven grid refinement of upper mantle PN and upper mantle velocity gradient in Israel and the Middle East using PN and PG waves, and she was able to refine down to a level of 1/8 of a degree in some places. And the paper shows that they successfully imaged smaller velocity features and improved travel time prediction in the region. And I want to stress that the purpose of this model is for improved travel time prediction. We're all about reducing the uncertainty in our locations. So any model results that we get for velocity and gradient, it's a very happy circumstance if they mimic what we know about the geology and look very similar to other models, but our primary goal is reducing the travel time uncertainty. So it's regions such as Western US, Europe, and the Middle East and East Asia have very high density coverage to improve travel time prediction. And so this is just kind of showing a ray density for the 1 degree grid, and we're going up to, in some of these grids, 10 to the 5th. And once we go down to 1/4 of a degree, we're still getting up there with values around 10 to the 4th or so in some of these smaller cells. So we feel like this is going to justify our refining the grid in those locations. So the PN travel time data for this study is taken from the global compilation of seismic data that Mike Bonneau published in 2021. We're using ground truth 25 or better events. They were relocated using the Bayes lock routine. Events with focal depths above the MOHO, of course, because if it's below the MOHO, you're not going to be getting head waves. So we restricted ourselves to shallow events, and we removed phase arrivals whose travel time residuals exceeded 3 standard deviations from the mean. The global map of tessellation points that we ended up with is shown in that global map on the lower left there. And where it's blank and doesn't have pretty colors, it was left at 1 degree. And you can see the 0.5, 0.25, and 0.125, the areas that we were actually able to reduce the grid size. So grid sizes were refined from 1 to 0.125 while adjusting smoothness and damping values using L-curve tests for upper mantle velocity and gradient. High damping value was used for cells that had fewer than 300 crossing rays. Suitable damping and smoothing values were determined at each grid level. Initially, we addressed the upper mantle slowness, and then we held that constant and addressed the upper mantle gradient values. And so you can see at the different grid levels, these are the damping and smoothing values that we optimized using the L-curve. So changes to travel time residuals from 1 degree to 0.125 degrees. The RMS-PN travel time residual changes with each grid refinement. So the original data, which shows in blue there, and then in red we're showing the data that for arrivals that are common to all grid refinements due to outlier removal. The RMS of the PN travel time residual was reduced by 7.6% from 1 degree to 0.125 degrees. And at 0.125 degree, or an eighth of a degree grid level, we still had, after the data reduction, 8,000 stations, about 62,000 events, leaving us with about 1.1 million ray paths. So to validate this, we held back 1,395 validation events. They were not used in the tomography so that we wouldn't have run the risk of a circular problem. And these were all ground truth 5 or better events that were used for the validation. The median mislocation for these events, the reduction in mislocation for global arrivals in the 0.125 grid, compared to AK135, we were able to reduce that by 33.5%. Compared to the original 1 degree RSTT model, which was already improved over AK135, we still improved it by 16%. The median mislocation reduction specifically for Europe and the Middle East arrivals and the 0.125 grid was a 32% reduction from AK135 and a 21% reduction from the original 1 degree RSTT model. Globally, most of the validation events were recorded by fewer than 6 stations. But you can see in the plots on the right how the different models performed in terms of the mislocation of these validation events. We also did some checkerboard tests just to look at our sensitivity, and we've got contiguous US and Europe and Middle East for, on the top we've got upper mantle velocity, and on the bottom we have upper mantle gradient, and you can see where we were able to recover the checkerboard, and admittedly it is pretty smeary in some places. And that has to do with the predominant direction of the ray paths that remained after we did the data culling. And so that was velocity, and that was the Western US, and this is Europe and the Middle East. And the grid refinement in the contiguous US, upper mantle PN velocity at the different grid levels. And again, I want to stress, we're not looking for adherence to known geology per se, although we're actually able to recover a lot of what we know about the geology. Our primary goal, again, is to reduce the travel times, uncertainties. And then in the this is for the upper mantle PN gradient. And again, we are getting some more detail here. At the different levels, some of the larger features are pretty persistent. The smaller features are starting to show up when you get down to the 1/8 of a degree level. In Europe and the Middle East, the upper PN mantle velocity at the different grid refinement levels pretty much mimic what we've seen in other models, although we get a lot more detail when we go down to 1/8 of a degree, which is panel D. And the PN gradient, which looks more or less like what we would expect. We're getting relatively high gradient in the vicinity of the Rhine-Graben and the subduction zone near Cyprus. And we do get more detail as we go to finer ray density, or finer grid cell density. So in conclusion, the high PN ray density in the Western US and Europe and the Middle East and East Asia enables systematic global grid refinement for up to 1/8 of a degree, about 14 kilometers per cell, using the RSTT model. The L-curve method was used to identify appropriate damping and smoothing values at each grid level, both for upper mantle velocity and then mantle gradient. The RSTT grid refinement improved the PN travel time prediction by 33.5 and 32.4 degrees or percent globally and in Europe and the Middle East respectively compared to the AK135 model. Smaller features are better delineated in the upper mantle velocity and gradient when we go to the finer grid cell where the data allows it. And future work includes modeling SN, PG, and LG using the grid refinement. And I forgot to mention that in this initial work, we're only addressing PN. So we have yet to look at the other phases. So acknowledgements, this research is supported by the GNDD program, Office of Nuclear Verification. Current RSTT model uses starting model, which was used as a starting model for the study, can be found. There's a website where you can find the global RSTT model, the 1 degree one. And the seismic bulletin data were obtained from public sites such as the IDC REB, United States Geological Survey, and the ISC. And that's not me. Okay. Thank you.
Thank you, Charlotte, for the very interesting presentation. So, any question here? Yeah, gentlemen.
Sorry. Thank you. Thank you for the excellent talk. I have observed that there is no much coverage of the East African rift, which I would assume that it's because of lack of data or coverage. In that region, we are having serious problem of having a reasonable travel time curve for locating earthquakes. So, but there are some active volcanoes, which I would assume maybe ground truth events in for 525 or something. So, is it not possible with some reasonable error to have a reasonable approximate RST travel time curve in that region? I mean, though there is some problem of the resolution and quality of data, is it not possible? We are really having problem of getting reasonable crystal structure for earthquake location. Thank you. If you can comment on that.
Yeah, we are not addressing the crustal structure here. We are only looking at the upper mantle slowness and the upper mantle gradient, but by and large, what we would need is an adequate number of regional phases. So if you have a local network and you have very close in PNS, those are not addressed by the RSTT per se, although they might be useful to help refine the crustal model in that area. Likewise, we can't really employ teleseismic arrivals. This is strictly for the regional, which is between 2 and 18 degrees.
Yeah. Just one quick question. Can you mention something about how did you come up with your collection of GT events? Your catalog for the GTs?
Well, a lot of these have been well defined as GT, both in the REB and in other data sets. The location uncertainty for those events would be less than, epicentrally, less than 5 kilometers. And so those are the events that we use as GT. Some of them are explosions or very large earthquakes that we know, we have great confidence that these locations are quite accurate. And so out to 5 kilometers, these are what we got from the catalogs in terms of the quality of the solution.
Okay, thank you. We got a question from our online attendees. So, is any comparison of this velocity model with other tomographic models, especially in terms of resolution?
We certainly looked at the other models, and we were pretty well convinced that what we see parallels what was found in other studies. But the other studies, generally speaking, I don't think solely and explicitly relied upon regional phases, and I don't know personally exactly what their grid size was.
Okay, thank you. We should move. One more question.
Thank you very much for your great presentation. My question is two. The first one is grid size. Based on the grid size smaller, the result better. So what about the smallest grid size do you think? That is the first question. And second one, you combine the three different organization catalogs for ISC, REB, and USGS. For the same event, which catalogs selected for the tomography or the calculation of the travel times?
I was not involved in that part of the work. However, I think the ones that exhibited the highest confidence for the locations with the highest number of arrivals would likely be the one that was used. Generally speaking, for high arrival events, you're not going to get a lot of difference in the location quality among the different catalogs.
Well, I think we should move on to the next. Okay, let's thank again speaker.